Hi, in this last lecture of the module 6, we are going to talk about a couple of really cool things. And there are tons of YouTube videos that you can actually show to your students, or you can actually do some of the experiments with these. So the title of this lecture is aerosol, but really what we are going to talk about is questions like, for example, why sky is blue and sunset is red, and how the rainbow comes about. So the physical principle behind all these is the light scattering. So remember, air is a gas, and gas are made of molecules. And it turns out when the light passing through these air, these tiny molecules will scatter some of these the lights. And particular type of a scattering is called the Rayleigh scattering, and this is exactly what we are seeing. This is when the particle that the scatterer is actually much smaller than the typical wavelengths that you're seeing. But one important aspect of this is that it scatters a blue light more than the red light. So let's see what that means. So let's actually so suppose you are standing at a surface. So there's Earth here, and there's an atmosphere right there, and light, sunlight is actually coming, and you're looking at, you're standing here, and as sunlight is actually passing through the air, it loses sort of a blue part of the colors. They're because they are scattered, and as a result, it becomes redder and redder and redder. Okay, so this is what the Rayleigh scattering do, and this is the reason why this happens is because the sunlight actually, which contains all different color, actually going through the air. And it doesn't really matter what the air is made of. It's just as long as there's an air with the tiny molecules, this will happen. So if you're looking up, not directly toward the sun, this is a sun here, then when you're looking up, you're basically seeing the blue lights, that is scattered lights out of the sun. So you're looking at, you perceive the sort of kind of space that the above you as a blue color, because these are the lights that are actually scattered toward your eyes. But when the sun is actually low and you're looking toward the sun, because the sun actually passing through the air, that it actually becomes redder. Now, but then you may actually ask a question about why don't we actually see the red sun all the time, but only seeing in the morning and the evening? Well, the key point here is that when the sun is rising and sun is setting, the light actually goes through, let's see, it's sort of froze at the moment. Light goes through a longer distance in the air. So let me actually draw that picture. So remember, Earth is round. So when sun is high up, right there, for example, and when you're looking up like this, the depth of the sunlight passing through is basically a thickness of atmosphere. But when sun is actually at the lower either sunrise or sunset, when you're looking at your sunlight has to pass much longer distance. Therefore, it loses much more blue light. Therefore, when it reaches your eyes, it actually looks much redder. That is the reason why sunset looks redder and the sky is blue. For astronomers, this can be a useful tool if the color of a sky actually tells us something about the composition. But as I said, the blue sky, the fact the sky is blue is nothing to do with which molecules or composition of the air is. Therefore, this is a sort of a generic property. But then you may actually ask why the picture of the Martian sky is not really blue, but it's sort of kind of reddish hue. It turns out the reason is because they're so dusty placed, you're actually seeing the dust hovering on the air, and essentially it reflects the color of the dust. But you can actually see some other sort of scattering effect when the particle particle size and the composition can be actually analyzed. And so in this particular slide, you don't really need to know too much about this slide, but I just want to tell you that these sort of a color of a skies and color of a clouds and all these things can be used to study the composition of the atmosphere sometimes. So enough about blue sky and the red sunset. And indeed, the best way to teach that subject is actually doing an experiment with the fish tank. And I have that video that is actually linked on the classroom. And please watch that one. That's actually really a simple demo that you can actually show to students that, give them a basic concept of that. So please check out those YouTube videos. And if you just type in "Why Sky is Blue" in the YouTube, that you can actually find tons of videos like that. So let's move on to the rainbow here. And to talk about the rainbow, we actually need to learn a little bit about the geometric optics, especially the concept of a reflection and the refraction. So when light passes through two different medium, at the interface, two types of things can happen. One is called the reflection. It just basically bounces back from the surface, like in this case here. The laser light go in and reflect back out. But also at the same time, refraction can happen, and that means the path of a light is not really straight, but it's actually bended a little bit, like that. But the important thing is that amount of a refraction depends on a color. So for example, in this case, I don't know whether you can actually see it clearly, but if you actually have a blue and the red lights like that and the yellow, the amount of bend at the prism, which is just the crown glass right there with the air, it depends on a color. It depends on actually a wavelength here. So that's an important thing to remember. But also, this particular picture shows a very interesting phenomenon called total internal reflection. So in the yellow light or the red light here, you can actually see, so when it goes from the air to the glass and glass to the air, you actually see sort of kind of double refractions. Refractions happen twice. But in the blue light case, when it goes in at the surface interface of the glass to the air, instead of going, the light goes out, it actually reflects back into inside. And that's exactly the key point of a rainbow here. And this total internal reflection is a really, really cool effect. And you can actually find many, many interesting demos about those. So for example, this particular one is actually showing a rather boring but important sort of demo about the the reflections and refractions together, and by carefully changing, you can actually see how the reflections and refraction happens. And I will actually link all these. So you can actually see, for example, here at this particular angle, light goes in and refracted out. So this is really with the glasses here. But if the angle is large enough, for example, at some point, it hits the point when the light is going in, and instead of refracted out, it will be reflected back in. So that's what something called the total internal reflections. And really cool demo for that one is something called a light fountain. This is when the laser light is actually totally reflected back in into the light, water stream, or it's water with typically some sort of a solution. But if you actually see it, for example, the water flows out, and you can see the laser light, which is supposed to go straight, is actually bounce back and forth and bounce back and forth, and just basically follow the water line here.
Liquid flow all the way to the bucket. Amazing. It does this because of total internal reflection.
And you can actually see these sort of kind of laser bounce back inside the stream, and this is exactly the fundamental principle behind our optical fibers. Fiber optics is just nothing but the glass, and in some sense that it can bend light in any shape so that they can actually follow these optical cables. And that's sort of every home has these optical cables that you probably to watch the TVs, or the audio cables and so on. So that's total internal reflection is one of the fundamental principles. And the really cool video, I think that's a sort of kind of fun video to watch, is at the beginning of this particular one that actually shows a kind of a laser show with the total internal reflections like that. So you get the idea of the total internal reflections. Now, how that works with the rainbow? Remember, rainbow typically happens right after the rain, and it always happens the opposite side of the sun. So after the rain, you actually have a lot of suspended water vapor, the water droplets suspended in the air. And if you're actually looking in an opposite side, so that side, left-hand side, is the sun, and the sunlight is coming in. And when the sunlight is actually hitting these water droplets, the property of the water is in such a way that when the light is going in, it's refracted in, but it actually, the geometry of the water droplet, which is a spherical typically, is in such a way that when the light goes in, it actually internally reflected at the opposite side back out. So instead of this light actually just basically completely goes through, the light goes in and hit the water vapor, and it sort of kind of come out with a different angle. And as I said, the angle of refractions will depend on a color. So what happened here is that when the sunlight that contains all the different spectrum that goes into the water droplets, when it comes out, the different color comes out with a different angle. So it's sort of kind of spread out, and you can actually see better in this particular graph, that detailed picture, that when the sunlight with all these different color mixed together goes in, they're all refracted in a different sort of angle. So when it comes out, the red is actually at the sort of a bottom, and the blue is actually top. So that's why that you actually have this rainbow pattern. Now you're wondering that, well, but we're not really looking at the one water droplet. Yes, you're actually looking at the many different water droplets in the opposite side of the sun, and the rainbow that you're seeing is the combination from all these different lights here. And you're looking at, this particular parts of air is full of these refractions, right? But the angle that this one makes is a very specific. It's about 42 to 40 degrees right there. And the lights from the only the ones that are in the right positions, so this angle will makes the lights falling into your eyes are the ones that you're actually seeing. So even though the every water droplets in this side, like these, for example, will reflect back the lights, you're only seeing a very selective sort of band of the droplets with, say, roughly about 40 to 42 degrees ring of the rainbows are the ones that you're seeing. So that is the reason why the rainbows are sort of kind of arch like that. And if you don't believe me, then this is probably a cool picture. Rainbow is really the circular. And the reason why we don't really usually see is because, there's a ground there. And this guy was actually jumping off the plane and is essentially, skydiving, and in a sort of kind of the oceans in the Hawaii. The air is pretty humid, has a lot of water droplets, and his sun is actually sort of kind of his back. It's very high up top there. And when he jump and take pictures like this, you're actually seeing the totally internally reflected, but also dispersed different color of lights from the water droplets. Of course, the lights are, again, from the everywhere in the air, but the one that falls into your eyes has to have a very particular geometry, the positions to make these particular color of lights going into your eyes. So you can imagine that as you fall, you'll keep seeing these rainbows, but of course those rays are coming from the different droplets, but the whole shape of the rainbows are maintained. Rainbows can be actually very useful for the astronomers because it turns out the size or the angle of the rainbow makes depends on a particular composition of a cloud. So for example, on a Venus, when you can actually study the shape or the size of a rainbow, and you can guess what is the material that produced this rainbow by studying something called index of refractions. And from there, you can actually guess the composition of a cloud of a Venus is a sulfuric acid, for example. And the Jupiter also has a very different, set of clouds, and we will actually talk about it later a little bit more, why it actually has a band structures like that. But again, study like these will tell us a lot about the composition of these clouds that we actually know. Some of them are like ammonia, and some of them are water, and some of them are sulfuric acid and sulfur compounds and so on. So you can actually study, and we can find out a lot about the outside of atmosphere and the composition of the clouds by studying things like these. So again, as I said, this particular chapter, which is indeed especially about the clouds and the rainbows and the skies, are very good activities, and it's actually very easy to produce in your classroom. Also, I think the greenhouse effect and the discussion on the climate change is also a very important part. So this is a very science-rich aspect, parts of the class, but also I think that this is actually more directly relevant to your classroom too. And a really fun activity with the even younger kid is that if you actually have a spray bottle filled with the water, and in a sunny day, just go out and spraying those in the opposite side of the sun, then you will see the rainbow pattern created simply because those water droplets will totally internally reflect the sunlight, and kids will have a fun with that one. Okay, so that wraps up the module 6, and in the module 7, we are going to talk about the motion of these air with what we call as a wind.